Hi, this is the preview lecture for lecture 8, and we'll have a really short video for this preview lecture. Up to now, we have talked about the Poisson equation. And we have found that eventually we have to able to solve nonlinear equations. And in the previous lecture, lecture 7, we did it. So we have applied our Newton-Raphson method to some small problems. And today we will apply it to the realistic problem, the Poisson equation. However, the nonlinear term in the Poisson equation is really localized. So when you have a look at the residue vector, its isentry Ri can be written as this is corresponding to the Laplacian part, and this is corresponding to the doping dependence, and this is corresponding to the contribution from electrons. And you can easily find that this is nothing but Qn, which is integrated over our control volume. So in this case, it is xi minus 0.5 to xi plus 0.5. So the control volume of our ice grid point. And you can find that since this is just given as a local function, when we take the Jacobian matrix, then it becomes easily calculated. When you define the Jacobian matrix and its I, j term as round Ri over round phi j, then from this nonlinear term, we can have only the contribution like j, I, I component. It is because in this term, we have only the terms like exponential of something like q phi I kbt or something like this, delta x q and I. So when we take the partial derivative with respect to j, if I and j are not the same, then it will give us just number 0. We will have the non-zero contribution from the electron density term only when j equal to I. Simply speaking, when we take the Jacobian matrix, here we have black colored one, which is obtained from our previous implementation, and this newly introduced electron contribution written in red, and it contributes to ji, I component. And since we have just exponential term, it gives q over kbt in front of it, and that's it for all this evaluation. So compared with our previous Poisson equation, the only difference is now we have this red colored term, which really depends on, once again, the phi I itself. It means that if we evaluate the Jacobian matrix at a given Newton iteration, then it will change at every iteration. So Jacobian matrix cannot be reused, and every time we have to build it, because that has certain term which really depends on the solution, which can change at every iteration. The implementation is quite straightforward. So these are just defining variables, and here we have 6 nanometer thick structure, which is corresponding to 0.5 nanometer of one oxide and 5 nanometer thick silicon and another 0.5 nanometer thick oxide. This is the given structure used in our example, and in your homework please use different numbers like this. So oxide thickness is increased to 0.8 nanometer instead of 0.5 nanometer. Well, everything is just same as before, so I will just skip it. And here we have two parts which is related with Laplacian, and this is corresponding to our previous black colored component, and this is just independent on the solution. However, we have also red colored term which is corresponding to the charge density, so we have to consider this term too. So this is written here as a charge part or charge term. When you have a look at the residue and Jacobian matrix, then we can find the additional term related with electron contribution. So it's a partial derivative with respect to the diagonal component phi I is also shown here. Please check it. And here we have two special consideration for interface nodes. As I told you before, since our electron is existing in the silicon material only, so half of our control volume is assigned to silicon and half of it is assigned to oxide for our interface node. That's the reason why here we have a factor of 0.5 to consider the reduced control volume. So let's have a look at the pseudocode for full code. Okay, so first copy and paste our defining variable part. You have many variables. We start from the phi whose components are all just 0.33, which is satisfy the boundary condition. So boundary condition itself is satisfied, but inside the silicon channel, the Poisson equation is not satisfied. Okay, so it is not the best initial guess, but anyhow we will use it. Later we will talk about how can we improve initial guess for our potential. After that we have Newton loop, and here we just learn 10 times of Newton loop. So we have not introduced the way to break the loop when we have a certain small update values. So just to learn sufficient times. 10 iteration is enough for this case. And here Jacobian matrix and residue vector are constructed here, and please copy and paste it to here. You will have it. After that your update vector is obtained by just Jacobian and minus times residue. You understand this one. Jacobian matrix times update vector should be minus residue vector. That was our general form for Newton-Raphson method. So you just solve it and just add your update vector to your present temporal solution, and you will have the updated potential. So please plot it as a function of a position, then you will have a certain phi which just looks like in this way for given gate bias and change the gate bias. Okay. So now you have homework. Since we have Korean Thanksgiving Day in this week, so your homework due is now postponed to the next Monday morning. So please enjoy your holidays. And the goal is just to write nonlinear Poisson solver for the double gate structure. Compared with our example shown in this slide, only difference is the oxide thickness. Please use more realistic 0.8 nanometer for your calculation. And after the calculation is over, then please show the integrated electron density, which is written in the unit of per centimeter as a function of the gate voltage. Maybe you will find certain things. So gate voltage and your integrated electron density per centimeter unit shows something like this in the linear scale, if this is written in linear scale. And please provide a second graph where the y-axis is written in the logarithmic scale too. So this is a semi-log graph and this is a linear graph. So suggested voltage range is just the same as before, from 0 to 1 volt. I have one caution about this homework. If you directly jump into 1 volt, then certainly you will fail. Please do not try this in your homework. So then how can you proceed? First, solve 0 volt. You can easily solve it. You can easily obtain the solution for 0 volt. After that, just to try 0.1 volt, slightly increase gate voltage. In this case, the converged solution at Vg equal to 0.0 volt is used as the initial guess for your new bias condition. And let's assume that now you have the converged solution for your 0.1 volt. Then what will happen? Now, by using this solution as an initial guess, please try to point to 2 volt. After you have succeeded to find the solution, then please move to 0.3, 0.4, and so on. So this procedure is called bias lumping, and this is quite important for realistic implementation. You cannot directly achieve your final bias point. So unfortunately, you have to introduce many intermediate steps to your final target bias voltage. Then you have to solve many intermediate steps. So please do so. Don't try to solve 1 volt directly. Okay, this preview lecture for lecture 8 is particularly short because we will do some exercise in the actual lecture. And you have homework number 8, and please do it. I think that this is very important first milestone for your entire semester. Once you can achieve this nonlinear Poisson solver and you have the basic knowledge on the computational microanalysis. Okay, see you next Monday. Bye.